What if infinity isn't real? What if it's just an illusion, a byproduct of the universe's own finite processing power? This episode explores computational infinity, CI, the idea that all infinities, whether never ending or never starting, are just different manifestations of the same computational constraint. From black holes to quantum physics, from AI's struggle with infinite context to the hidden structure of prime numbers, get ready for a mind-bending journey through some seriously deep concepts. It's a brilliant thought experiment with kernels of truth, but it's not yet a fully fledged theory. It's more of a provocative hypothesis begging for research. Exactly the kind of spark that could inspire real breakthroughs. Buckle up. You're watching Computational Infinity.
You think you understand infinity. Really? Okay, get ready, because what if I told you that the universe might be like hacking infinity?
Hacking infinity?
Yeah, like it's running a program, but the code's all like this infinity thing, it's cool, but I've only got so much RAM, let's just round these infinite things off.
Okay, I like where this is going.
Today we're going on a deep dive into a wild idea, computational infinity.
It's a fascinating concept, and it really challenges how we think about infinity, especially now, in a world dominated by computers and calculations.
Okay, so before we get too far down the rabbit hole, let's just lay out what we're dealing with. When we say infinity, what are we even talking about?
So traditionally, you've got two main flavors of infinity.
Flavors. Okay, I like this.
First, imagine those never-ending decimals, like pi, right? 3.14159, and it just keeps going forever.
Yeah.
That's what we might call terminating infinity. It's got a starting point, but no finish line.
Okay, so it terminates at infinity.
Yeah, you could think about it that way. Then there's the non-originating infinity.
Okay, this sounds even weirder.
This is where things get really trippy, because it's a sequence that, conceptually, has no beginning.
Mm-hmm.
Think about dividing 1 by increasingly larger and larger prime numbers.
Okay.
That string of digits, it just keeps going, both backwards and forwards.
Whoa, so no start and no end.
Yeah, no start, no end. It's kind of mind-boggling.
Okay, so two sides of the same infinite coin.
Yeah, maybe.
But how do we even begin to think about the universe rounding these infinities off? I mean, it's like saying the universe is doing some cosmic bookkeeping just to, keep reality running smoothly.
That's a great analogy, and that's where things get really interesting. To grasp this, we have to kind of dip our toes into category theory.
Oh boy, category theory. This is where I usually start to get lost.
No. Don't worry. It's not as intimidating as it sounds. Think of category theory as it's like a way to find family resemblances between different mathematical concepts. It's like spotting the common DNA between, say, a zebra and a horse. You're basically looking for that underlying structure and seeing how things connect.
Okay, so instead of getting bogged down in the specifics of endless decimals or prime numbers, category theory gives us a bird's eye view.
You got it. We can see the whole forest, not just the trees.
I like that.
And that's how we start to see how these different infinities, the terminating and the non-originating, they might be more alike than we thought, especially when we consider the limitations of any computational system.
Even a universe-sized one.
Even a universe-sized one.
Wait, hold on. Are we really saying the universe is like a giant computer?
Well, think about it this way. Any computer, no matter how powerful, has limits.
Right.
Limits on storage. Limits on its processing power. It can only represent numbers with finite precision. So even with something like pi, with its infinite digits, at some point, you got to chop those digits off. You have to round.
So even though pi theoretically has an infinite number of digits, in any real system, it becomes like a chopped off, rounded version.
Precisely. And that's where the distinction between our terminating infinity and non-originating infinity starts to get blurry. In a computational system, they both hit a wall, like a rounding error, a limit.
Okay, I think I'm starting to see where this is going. We need a new way to look at infinity.
Right, a new way, yeah.
A way that takes these computational limitations into account.
Exactly, and this is where our new friend, category theory, comes in. We can use it to create a new category specifically to represent infinity, but as it exists inside a computational system. We can call it computational infinity.
Computational infinity?
Or CI. For sure.
CI, got it.
It's like we're creating a special map of infinity. But it's a map that knows about the limitations of any computer trying to handle it.
So we've got our two traditional infinities, right? But when we put on our computational glasses, they both get a bit fuzzy around the edges.
Yeah, they both end up in this CI category.
Okay, but what does that actually mean?
Here's the kicker. Within this CI category, those differences we talked about, between never ending and never starting,
Yeah.
they might not matter as much as we thought. Think about it this way. Imagine you're looking at a map of Earth from far away.
Okay.
As you zoom in, you see all the detail, the
Yeah.
curves and the contours of the coastline.
Right.
But as you zoom out, all those details start to disappear. And those coastlines, they start to look like straight lines.
Ah, I see. So you're saying that different types of infinity are like the coastline. Up close, they seem totally different, but from a zoomed out perspective, they start to look the same.
Exactly. And that zooming out, that's like taking into account those computational limitations. We're not saying infinity isn't infinite. We're just saying that in a computational system, those different flavors of infinity, they might converge into something, well, more manageable, something that can actually be processed.
Okay, this is mind-blowing. We're basically questioning the fabric of reality here.
We are, and we're just getting started. Remember that mapping between categories I mentioned earlier?
Yeah.
We can actually think of a mathematical tool called a functor. It's a specific concept from category theory.
Okay.
This functor takes those traditional infinities, and it doesn't matter if they're terminating or non-originating, and maps them into our new CI category.
So this functor is like the ultimate cosmic translator. It's saying, hey, I know you infinities think you're all special and different, but in the grand scheme of computation, you're all just dot computable.
I love that. That's a great way to put it. And this brings us to one of the most mind-boggling equations in math. 1 plus 2 plus 3 plus 4 minus 112.
Wait, what? How can adding all the positive whole numbers equal a negative fraction? That's just wrong.
Well, not exactly. It's a result that comes from a process called analytic continuation. It's kind of like stretching a function beyond its original boundaries, a way to make sense of something that seems impossible.
So like how a flat map can represent a round Earth, even though it seems totally counterintuitive.
Yes, exactly. We're stretching our mathematical tools to make sense of the infinite.
Okay. But how does this equation fit into this whole computational infinity thing?
Well, some mathematicians believe that this seemingly absurd result might actually be a clue, a hint that the universe itself is doing some cosmic analytic continuation, some rounding off when dealing with infinity.
So what you're saying is that this equation, this 1 plus 2 plus 3 plus 4 minus 112, might not be a mathematical paradox, but rather a glimpse into how the universe computes infinity.
That's one way to look at it. And that's just the tip of the iceberg. If we're right about this, then there's a whole bunch of other mathematical and physical weirdness that might start to make sense when you view it through this lens of computational infinity.
Okay, I need a minute to process all this. We've gone from different types of infinity to category theory, mind-bending equations, and a universe that might be doing its own magic tricks. This is a lot to unpack.
I know, but don't worry, we'll take it step by step. Next time, we're going to explore how this concept of computational infinity might actually be playing out in the real world, in places like black holes, quantum physics, and maybe even artificial intelligence.
Oh boy, I can't wait. This is like a roller coaster ride through the deepest mysteries of the universe, and I'm strapped in and ready for the next loop-de-loop.
I love it. Buckle up. It's going to be a wild ride.
Okay, so we've laid the groundwork, right? We're talking about this whole idea of computational infinity, the universe maybe, like putting limits on infinity, like a cosmic budget for weirdness.
Yeah, like a cosmic budget. That's good.
But where do we actually see this playing out? Like, where's the evidence?
Well, one place to look is where physics, as we understand it, starts to kind of break down.
Okay.
Those places where we hit these infinities that don't really make sense. Take black holes, for example.
Black holes, yeah. Those are always fun. Massive objects, huge gravity wells. Not a good place to have a picnic.
Right.
But how do black holes even tie into this idea of computational infinity?
Well, at the center of a black hole, according to our current theories at least, you have a singularity, right?
Right.
And a singularity, it's a point of infinite density. All the matter crushed into an infinitely small space.
Yeah, singularities. Those are always a bit of a red flag in physics, aren't they? Like
Yeah.
the universe is going, error, does not compute.
Exactly. And that's where CI might come in.
Okay.
What if those singularities, those supposed points of infinite density, aren't actually infinite?
Okay, yeah, what if?
What if they're just the universe, like hitting its computational limit?
Like a computer program trying to divide by zero. Oh, I see. So instead of a true infinity, a singularity might just be the universe saying, look, I can only crunch numbers so far. This is as close to infinity as I can get.
Precisely.
Yeah.
Our models, the ones we use now, they might be showing us an infinity because they don't take into account these the universe's computational constraints, you know?
Yeah.
It's like trying to draw a perfect circle on a pixelated screen.
Oh.
You can get close, but you eventually hit the limit at resolution.
So those infinities we see in black holes might not be real infinities, just a sign that the universe is doing some serious rounding behind the scenes.
Yeah, some cosmic rounding.
But hold on, isn't this all just speculation? Like, we don't actually have proof the universe is making these rounding errors, right?
True, yeah, it's still early days for this whole idea.
Mhm.
But think about it. If the universe is a computational system at its core, there have to be limits.
Okay, yeah.
And those limits, they would inevitably affect how infinities are handled, you know? It's a matter of logic. It's how any computational system would have to operate, even a universe-sized one.
Okay, yeah, I see what you're saying. It's not that we have, like, direct evidence of these rounding errors, but the idea itself makes sense when you consider the nature of computation. So where else might we see these computational limits playing out?
Another place is quantum field theory.
Quantum field theory.
The framework we use to describe the behavior of all those subatomic particles. Even there, we encounter these, well, pesky infinities, and physicists have to find ways to tame them.
Quantum physics has always been a bit mind-boggling to me. It's like the rules of reality just go out the window at the subatomic level.
Right. And one of the biggest challenges is dealing with those infinities. They pop up when you try to calculate certain things, like the energy of a particle.
Yeah.
The physicists have these techniques, like renormalization.
Renormalization.
Yeah. But it's always felt a bit like, I don't know, like sweeping the problem under the rug.
It's like they're saying, okay, we got this infinite answer. Let's just tweak the math a bit and pretend it's a finite number.
Exactly. But with CI, these infinities might not be problems to be solved, but more like clues to a deeper reality. What if those infinite energies aren't a fundamental property of the particles themselves? What if it's just, another consequence of the universe's computational limits?
Like the universe saying, hey, I can only be so precise, working with a finite amount of bits here.
Exactly.
Yeah.
I'd explain why this renormalization thing, why it even works. Even though it seems kind of ad hoc, it's basically a way to incorporate these computational constraints into our calculations, even if we don't realize we're doing it.
Okay. So we've got black holes, we've got quantum physics. Any other places where this computational infinity idea might be shaking things up?
Well, remember that equation we talked about, the 1 plus 2 plus 3 plus 4 plus 21, 12?
But that makes no sense.
It actually has applications,
Yeah.
real-world applications in string theory.
Wait, seriously. That equation is used in actual physics.
It is. It's used to calculate the energy of certain vibrating strings, which are, the fundamental building blocks of matter, according to string theory.
Okay. Now I'm really starting to feel like we're glimpsing something profound here. It's like this crazy mathematical result, the one that seems to defy all logic, is actually a hint about the underlying structure of reality.
It might be. And that's why this whole concept of computational infinity, it's so exciting. It has the potential to bridge the gap between, abstract math over here and the physical world over there.
Yeah, it's like we're seeing those equations, and they might actually be describing the fabric of the cosmos.
And that fabric, it might be a lot more computationally limited than we thought.
With those rounding errors playing a much bigger role.
Way bigger.
This is a pretty humbling thought.
It is.
It's like we're realizing the universe might be playing by slightly different rules than the ones we thought.
A different rule book altogether.
But if this computational infinity thing, if it's so groundbreaking, why haven't we heard of it before? Why aren't all the physicists and mathematicians shouting about it from the rooftops?
Well, it's a relatively new idea.
Yeah.
And it challenges some pretty deep assumptions.
Yeah.
About the nature of math, about infinity. It takes time for these kinds of paradigm shifts to, gain traction.
Yeah.
Especially when you need a deep understanding of things like category theory.
Okay.
Yeah.
It's true. Not exactly a light dinner conversation, but that's what we're here for, to explore these ideas and make them accessible.
So where do we go from here? We've seen how CI might be showing up in physics, but you mentioned applications in other fields, right? Like artificial intelligence and
cryptography?
AI, cryptography. Let's start with AI. One of the biggest challenges in AI is dealing with infinite sequences, whether it's natural language processing, machine learning, or even just modeling how we think, how our brains work.
Yeah. Our brains are constantly processing like streams of data, making predictions about the future. But how do you teach a computer to do that when it has finite resources? It seems impossible.
It does seem impossible, right? And that's where CI could be revolutionary. Instead of trying to force a computer to handle an infinite amount of data, we could use CI to create algorithms that, work within those limits of computation.
Ah, I see. So instead of building AI that can somehow handle infinity head-on, we could design it to be more like universe-aware,
Universe-aware, I like that.
to work within those computational constraints that seem to be like baked into reality.
Exactly. We could move away from those brute force approaches, the ones that need massive amounts of data, massive processing power, and move towards, more elegant solutions that are more in tune with how the universe actually computes.
So we're talking about a whole new approach to AI, one that's informed by this deeper understanding of infinity and computation.
A whole new approach, yeah.
But what about cryptography? How does computational infinity play into that?
Well, cryptography relies heavily on prime numbers, especially really, really big ones.
Right. The bigger, the better.
The security of a lot of encryption algorithms depends on the difficulty of factoring large numbers, breaking them down into their prime components.
Right, because as prime numbers get larger, they become rarer. It's like trying to find a needle in an increasingly vast haystack. But where does CI fit into all of this?
Remember how we talked about how the universe might be like categorizing infinity, merging those never-ending and never-starting sequences?
Yeah. So, like, those large prime numbers, they might be seen as non-originating infinities because their emergence is so unpredictable. We can calculate them, but they kind of pop up in this random way.
Yeah, they do. So if the universe is operating under these computational constraints, it might be that those large prime numbers, their distribution, it's not actually as random as we think.
Okay.
There might be underlying patterns that emerge because of CI.
So you're saying that the foundation of our encryption systems, the thing we assume is based on the randomness of prime numbers, could actually be affected by these computational limits on infinity.
It's a possibility.
Yeah.
And one that we need to explore further.
If we could crack the code of how CI influences prime number distribution, that would have huge implications.
Huge.
For cybersecurity, for breaking encryption, for developing new methods, it would change everything.
But change the game.
This is getting pretty intense. It's like this abstract mathematical idea, this computational infinity, is suddenly touching on all these critical aspects of our world, from black holes and quantum physics to, the security of our digital lives. It's pretty wild.
It's mind-blowing, really.
Yeah.
And that's what makes it so profound. It's not just a mathematical curiosity. It's a fundamental shift in how we view things.
A shift in perspective that could ripple through every field, science, technology, maybe even beyond. If the universe is a computational system, what does that even say about us? About consciousness, free will, the nature of reality itself. Those are some deep waters.
Deep waters indeed. Maybe best left for another deep dive. But for now, let's just appreciate how far we've come. We started with this simple question. What if the universe is making rounding errors? And look where it's led us.
To a whole new way of thinking about infinity, about the limits of our knowledge, and about the very nature of the universe. It's like we've been given a glimpse behind the curtain, a peek at the computational code that might be running the show. But I have a feeling this isn't over yet. There's still more to uncover, right?
Oh, absolutely. We've only just scratched the surface of what computational infinity might hold. In the next part, we're going to go even deeper. We'll explore some of the philosophical implications, what it means for how we understand math, reality, and we'll even speculate about what other discoveries might be waiting for us as we continue to explore this uncharted territory.
Can't wait. This is one deep dive I don't want to end. It's funny, as we've been going through this whole computational infinity thing, I've been kind of wrestling with this feeling. It's like we're not just talking about math or physics anymore, are we?
What do you mean?
It's like we're bumping up against something much bigger, something that touches on the very nature of reality.
It's that sense of awe.
Yeah.
Right? When you start to realize those equations, those theories, they might not just be describing the universe,
Yeah.
but actually be reflections of its structure.
Yeah.
It's like we're seeing the underlying operating system.
Exactly. And this whole concept of CI, it really throws a wrench into how we normally think about mathematics. We tend to think of it as like this pure abstract thing, a world of, perfect forms, absolute truths.
Right, like those perfect circles and triangles from geometry class. Existing out there, independent of everything.
But CI suggests that even those perfect forms, when we start talking about infinity, they might actually be subject to those computational constraints too. It's like saying even those ideal shapes, they might have this like slight fuzziness.
Rounding error.
A rounding error, exactly, that we just haven't been able to see.
It challenges that whole traditional view of math as something that exists out there, separate from the physical world, CI is saying math might be way more intertwined with the universe than we thought.
So instead of math being this separate, pristine thing, it's actually playing by the same rules as everything else.
Maybe. It's like math itself has to fit within the universe's computational budget.
And if something as fundamental as infinity might be subject to these limits, then, well, what other mathematical concepts need to be revisited?
What other truths are actually just approximations, rounded off versions of a deeper, more computational reality?
It's like we've been working with this blurry map of reality all along, and CI is like a new lens.
New lens, yeah.
It's a way to see those subtle distortions, those rounding errors that we might have missed before.
And as we refine that lens, who knows what else we might find? What other seemingly impossible things will suddenly make sense?
This is huge. It's a complete paradigm shift,
Yeah.
and it could ripple through, well, everything. Science, math, philosophy. It changes how we understand the universe and our place in it.
Absolutely. And it shows how important it is to think across disciplines, bring those ideas together from different fields. Who would have thought that thinking about how computers handle infinity could lead us to these insights about the universe itself?
It's a good reminder that we're all part of this big intellectual adventure, this quest to understand the universe. And even if we never fully grasp the true nature of things, well, the journey itself is pretty amazing.
Couldn't agree more. And maybe that's the most beautiful kind of infinity there, is the infinity of human curiosity, that endless drive to explore, to question.
Yeah, that's a journey that never really ends. Well, I think we've reached the end of our deep dive for today, but this is just the beginning of the conversation, really. I encourage everyone listening to keep exploring these ideas, keep asking those big questions, and never lose that curiosity about the world.
Because who knows, the next big breakthrough might come from someone listening right now. Someone who's been inspired to take their own deep dive into these mysteries.
It's a great thought to end on. Thanks for joining us on this incredible journey. And until next time, keep exploring, keep questioning, and keep diving deep.
All right, deep divers, welcome back. You ready for round 2? We're going even deeper into computational infinity.
Oh, yeah. I'm excited to see where we go with this.
Last time, remember, we were like, what if the universe is kind of like a giant computer? Like, what if it deals with infinity in this finite, limited kind of way?
Yeah, that's right. Like reality has a RAM limit, so to speak. It's a wild idea.
Wild, but super intriguing. And this time, we're going to take that idea and see how it plays out in the real world. Okay.
Let's do it. I'm all for it.
So you've hooked me up with this stack of sources. We've got Wikipedia on this thing called co-induction, some seriously deep forum discussions, even a draft research paper someone sent you.
Yeah, some really cool stuff. It's fascinating to see how people from different fields are all running into these same questions about infinity. Like, it's everywhere, right?
Totally. And from what I've been reading, it seems like computational infinity, CI for short, could be like this master key unlocking all sorts of mysteries.
That's what it's starting to look like.
Black holes, the limits of AI, even the nature of reality itself. It's mind-blowing.
Yeah, no kidding. CI basically boils down to this question. What if reality itself follows the same computational rules that, our computers do?
Right, like the same limitations and everything.
Right.
Okay, so let's jump into it. Where do you even begin with something this big?
Well, how about we start with where infinity causes the biggest headaches for scientists?
Good place to start. Headaches are never fun.
Exactly. Quantum field theory, QFT, have you heard about that?
I've heard of it, but I'll be honest, it's always seemed a bit over my head.
Well, it's where physics gets really weird. But basically in QFT, physicists are trying to describe how particles interact.
Okay, like electrons and stuff.
Yeah, exactly. And the thing is, when they try to calculate certain values, like the energy of an electron, their equations often spit out infinity.
Infinity, but that doesn't make sense, right? How can something have infinite energy?
Exactly. It doesn't make physical sense at all. So physicists had to come up with a way to deal with these infinities.
So what do? Just say, okay, infinity, whatever, let's move on.
Pretty much. Well, not exactly. They developed this technique called renormalization.
Renormalization.
It's basically a way of subtracting those infinities, like in a very specific, systematic way.
Okay. But even if it works, it sounds kind of like a mathematical Band-Aid.
Yeah.
Like, are they just sweeping the problem under the rug?
Yeah, it's always felt a bit like a hack, like a clever trick, but without a deeper explanation.
Right. So where does CI fit into all of this?
Yeah.
Does it provide that deeper explanation?
It just might. What if those infinities in QFT aren't actual infinities, but like a sign, a symptom of the universe hitting its computational limits.
So kind of like when your computer tries to calculate a number that's too big and it just gives you an error message.
Exactly. Imagine the universe as like a computer with finite computational resources, and at a certain point it's like, whoa, this is too much, I can't handle this. And that's where we get these infinities popping up in our equations.
Whoa. So the universe is basically hitting its RAM limit, and we interpret that as infinity.
It's a possibility, right? And what's really trippy is that it suggests our equations, the way we describe the universe, might actually be reflecting its underlying computational structure.
Whoa. That's deep. Like our math is mirroring the universe's code in a way?
That's the idea.
Okay, mind officially blown. So if CI is right and the universe does have these computational limits, where else might we see evidence of that? What other problems could it solve?
Well, let's talk about something even more mind-boggling. Black holes. You know, those cosmic monsters where gravity is so intense that nothing, not even light, can escape.
Yeah, black holes are seriously freaky. And at their center, there's this thing called a singularity, right? A point of infinite density.
Right. But as we've been talking about, infinity is kind of a problem child. And with black holes, the problem goes beyond just the infinite density thing.
Okay, what else is going on in there?
Well, when something falls into a black hole, it seems to disappear completely. Like, poof, gone. Which really messes with a fundamental law of physics.
Which law is that?
The law that says information can never be truly destroyed. Quantum mechanics is built on this idea.
Oh, right, the information paradox. I've heard of that.
Mm-hmm.
So we have this clash between general relativity, which predicts these singularities, and quantum mechanics, which says information can't just vanish.
Exactly. It's a big problem. And this is where CI offers a really interesting perspective. What if those singularities, those points of supposed infinite density, aren't actually infinite?
You're saying it's another case of the universe hitting its computational limit.
Yeah, maybe. Like, our equations tell us the singularity is infinite, but that could be because our current model of space-time based on general relativity just breaks down at that point.
It's like the equation is trying to describe something beyond its capabilities, like trying to fit the ocean into a teacup.
Perfect analogy.
But that still doesn't tell us where the information goes. Right. Like, if it's not being crushed into an infinitely dense point, where does it end up?
That's where this other mind-bending idea comes in, the holographic principle.
Okay, I gotta admit, the holographic principle always sounded a bit too sci-fi for me.
It's definitely out there, but it basically suggests that all the information inside a black hole, everything that falls in, could actually be encoded on its surface.
Wait, what? So instead of being crushed into oblivion, the information is like smeared on the outside of the black hole.
Kind of. Think of it like a hologram.
Okay, so a hologram contains a 3D image, even though it's just a flat surface.
Yeah, exactly. And the holographic principle suggests that something similar might be happening with black holes. All that information, instead of being crammed into an infinitely small point, is represented on a finite surface.
Whoa. That's wild. But how does that even work? How can you fit so much information onto a surface? It's like compressing a movie down to a single frame.
Well, that's where the connection to CI gets really interesting. Remember, CI is all about finding ways to handle infinity within finite limits. And the holographic principle is essentially doing the same thing, just on a cosmic scale.
So the universe is basically running a super efficient compression algorithm on all the information that falls into a black hole.
It's a possibility, right? And if the universe is operating under these CI constraints, then this kind of holographic encoding might actually be necessary.
Like it's the only way to avoid those infinities.
Exactly.
Okay, this is seriously mind-blowing stuff. So we've seen how CI could explain those crazy infinities in quantum field theory and maybe even resolve the black hole information paradox. But where do we go from here? What other areas could CI shed light on?
Well, how about something a little closer to home? Something that might even impact our daily lives.
Okay, you've got my attention. What is it?
Artificial intelligence.
Okay, artificial intelligence, AI. I'm all ears, tell me more.
Yeah, so one of the biggest challenges in AI right now is this whole idea of infinite context windows. It's a big deal if we want AI to be more like us.
Okay, context windows, break it down for me.
Okay, imagine how we humans experience the world. It's like this constant flow, right? We remember stuff from the past, connect it to what's happening now, and use all of that to figure out what might happen next.
Right, we build on our experiences.
Exactly. But current AI models, they kind of struggle with that. They have this limited context window, meaning they can only process a certain amount of information at once.
Ah, so it's like those annoying chatbots that completely forget what you said 2 sentences ago. You're like, hello, are you even listening?
Yeah, that's a perfect example. And it all comes down to computational limits, just like those infinities we were talking about in QFT and black holes.
Makes sense. If the universe itself has computational limits, then obviously our AI is going to run into those same walls.
Exactly. Building an AI that can truly grasp infinite context, one that can learn and adapt from an endless stream of data without forgetting anything, it's a huge challenge. Like the computational power you'd need is just mind-boggling.
But wait, hold on. Isn't that what CI is all about? Finding ways to handle infinity within these finite limits?
Yeah.
Could that be the key to cracking this AI problem?
It could be, and that's what makes this whole CI thing so exciting. What if we could make AI that doesn't try to store absolutely everything, but instead learns to compress information, like really efficiently? Extract the essential meaning and relationships without getting bogged down in all the details.
Okay, pause for a second. I need to catch up. That sounds pretty abstract. Like, how would that work in practice? Give me an example.
All right, let's take language processing, for example. Imagine an AI trying to understand a conversation. Instead of remembering every single word, a CI-powered AI could learn to represent the underlying meaning of the sentences, the concepts, the relationships, all that juicy stuff.
So it's not about memorizing words. It's more like understanding the whole point of the conversation. Like reading between the lines, right?
Exactly. And what's really cool is that this compressed representation, it can be constantly updated with new information. It never hits a hard storage limit.
Whoa. So AI could potentially have a memory that's way more like ours. It could learn from massive amounts of information, remember all the important stuff, and keep adapting without forgetting.
Exactly. It could keep getting smarter and smarter.
That's both amazing and a little bit creepy, to be honest.
Yeah, I know what you mean.
But okay, let's switch gears for a minute. Let's talk about something a little less, I don't know, existential. How about cryptography? I always think about secret codes and spy stuff. How does CI play into all of that?
Cryptography, it's actually a perfect example of where the concept of infinity pops out in a really surprising way. You know that modern encryption relies heavily on prime numbers, right?
Prime numbers. Okay, back to high school math class. Those are the numbers that can only be divided by 1 and themselves.
Yeah,
right.
You got it. And the reason they're so important for security is that finding really large prime numbers is incredibly difficult, even for the most powerful computers out there.
So the longer it takes to find those prime numbers, the harder it is to crack the code?
Exactly. That's the whole basis of encryption algorithms like RSA, the ones that keep our online transactions secure. But here's where CI throws a bit of a curveball. What if the universe's computational limits, like those we've been talking about, what if they actually influence the distribution of prime numbers?
Wait, hold up. You're saying that our whole understanding of cryptography, which is based on prime numbers being kind of random and unpredictable, could be flawed.
It's a radical idea, I know. But that's what some of these sources are suggesting. If the universe is this giant computational system with inherent limits, then those limits could ripple through everything, even something as seemingly fundamental as prime numbers.
Okay, that's kind of terrifying. Could CI actually be used to crack codes? Or maybe even create entirely new ways of generating prime numbers?
It's possible. It's like this double-edged sword. It could expose weaknesses in our current systems, but it could also unlock breakthroughs in security that we can't even fathom right now.
It's like opening Pandora's box of math. Okay, but let's zoom out for a second. Think bigger picture. We're living in this age of big data, right? We're drowning in information, stock markets, social media, scientific research, you name it. How can CI help us make sense of all that chaos?
You've hit the nail on the head. That's where machine learning comes in. And that's exactly what we're going to dive into next.
Okay, I'm ready. Bring on the machine learning.
Okay, machine learning, let's do it. I feel like this is where CI could really make a difference. I mean, we're practically swimming in data these days. How can CI help us make sense of it all?
That's the million-dollar question, right? A lot of really smart people are working on that as we speak. The thing is, traditional machine learning, the way we do it now, it's all about these finite data sets.
Finite data sets, meaning like a fixed amount of data. Yeah, exactly. Like you feed the computer a bunch of data, it looks for patterns, and then it uses those patterns to make predictions about new data.
Right, that makes sense. But the real world is messy, right? Like it's not always so neat and tidy.
Exactly. Think about things like the stock market or sensor networks, social media, all that stuff. It's constantly generating data. like an endless stream of information.
So it's like trying to fit an ocean into a teacup.
Yeah, kinda. And that's where traditional machine learning models, they start to break down.
Because they need a clear beginning and end to the data.
Right. They can't just keep learning forever. At some point, they're going to run out of memory, or the calculations are going to get too complex, too computationally expensive.
Okay, so how does CI change the game? How can it help us deal with these infinite data streams?
Well, imagine a machine learning model that doesn't try to remember every single piece of data. Instead, it learns to compress information, like really, really efficiently.
Okay, so it's kind of like that holographic principle we were talking about with black holes. Extracting the essence without getting bogged down in the details.
You got it. It's all about finding the essential patterns, the relationships between things, without needing to store every single data point.
So it's not about memorizing everything, it's about understanding the underlying structure of the data.
Exactly. And because it's not limited by memory, it can just keep learning and adapting as new data comes in. It's like it never gets full.
Okay, I need an example. Give me a real-world scenario where this would actually work.
All right. Imagine you're trying to predict the stock market. Right now, you'd probably train your model on a bunch of historical data, like maybe the last 10 years of stock prices.
Right, so it has a fixed amount of data to learn from.
Exactly. But with a CI-powered model, you could feed it a live stream of market data. And as new information comes in, the model is constantly updating its predictions, learning, and adapting to the ever-changing dynamics of the market.
So it's like having a financial advisor that never stops learning, constantly refining its understanding.
Exactly. Or imagine an AI system analyzing medical records, looking for potential health risks. Instead of retraining it every few months with new data, you could have it constantly learning from the stream of patient records, getting smarter and more accurate over time.
Whoa, that's incredible. It's like AI that truly evolves alongside us, always learning and adapting.
That's the power of CI. And it brings us to maybe the biggest question of all. What about the universe itself? Does CI have implications for how we understand the cosmos?
Now we're getting to the really big questions. But yeah, after everything we've talked about, it feels like CI must have something to say about the nature of reality, the very fabric of the universe.
Right. Think back to when we talked about the Planck scale, the smallest possible unit of space and time.
Yeah, I remember. It's like the universe is pixels, right?
Exactly. And the fact that the Planck scale exists suggests that space-time might not be as smooth and continuous as we think. It might be fundamentally discrete, like a digital image.
So instead of this infinitely divisible universe, we have a universe built on tiny, indivisible units of space and time.
It's possibility, and it fits perfectly with CI. If the universe is ultimately discrete, then it can't be truly infinite. There's a limit to how much information you can pack into a finite space, even if that space is unimaginably vast.
And that inherent discreteness, those limits, could be the reason why we see the order and patterns we do in the universe.
That's right. It's like CI is baked into the fabric of reality. It might be why physical laws exist, why the universe expands in a predictable way, why there's a limit to how much entropy or disorder the universe can have.
Whoa, so CI isn't just some abstract mathematical idea. It could be the key to understanding why the universe is the way it is.
It just might be. It's like we're starting to see the universe's operating system, the code beneath reality.
This is incredible. We've gone from tiny particles to black holes to artificial intelligence, and it all seems to point back to this idea of computational infinity.
And we've only just scratched the surface. CI is a young idea, but it has the potential to completely transform our understanding of science, technology, everything.
Absolutely. To all our listeners out there, keep exploring these ideas. Don't be afraid to ask the big questions.
Yeah.
And most importantly, never lose that sense of wonder. Because the universe is full of mysteries, and computational infinity might just be the key to unlocking some of the most profound secrets of reality.